Hi, good afternoon, everyone. I'm very honored and super excited to be here and share the details of our project called the Global Analytical Robustness Initiative with you. This is a cross-disciplinary big team science project where we aim to map the analytical variability across disciplines and mitigate its potential harmful consequences. Why do we want to do that? You may have heard about the replication crisis in psychology, which is caused by many factors, and one of them is the lack of analytical robustness. I can feel your sentiment if you think that that's not a consequential problem. Actually, who cares if it turns out that the power posing doesn't have a positive effect on behavior or other random psychological findings turned out to be non-replicable? But in the next 673 seconds, I want to show you that you still need to care about analytical variability, because the lack of analytical robustness is first a cross-disciplinary issue, potentially affecting a large proportion of empirical studies. Second, because it slows down evidence accumulation and creates a lot of research waste if we do not deal with it properly. Okay, as you can see, I'm smiling on that blurry picture. I'm smiling because it was just taken before the beginning of my PhD. After that, I conducted an experiment which did not work. After I conducted another experiment, another, and plenty of others. And many of them failed. In all of them, I tried to build on prior published findings. Let's be clear, I don't want to try to complain about having failed experiments. I think that's the way science is supposed to work, and that's the process, and that's how we learn. I'm telling you all this because I'm convinced that the analytical uncertainty if the analytical uncertainty had been transparently reported in the papers that I read back then, I could have avoided some of these failures, saving years of my life and public research money as well. But it's not just me. Our team consists of early career researchers with different backgrounds. Rotem is a neuroscientist at Dartmouth and Tel Aviv. Maya is a statistician at Stanford. Felix is an economist at Innsbruck. And I am a psychologist at ALTE Budapest. We all share some struggles which really forced us together. The heart of the problem is the following. A typical scientific journal article in recent decades, at least in empirical social sciences, like psychology, economics, sociology, or marketing, only can contain one result from one or a few analysis pipelines. And the conclusions were also based on the outcome of this pipeline. Why is that a problem? Because researchers do have a lot of freedom when analyzing their data. They can decide how to deal with incomplete or missing cases, with outliers, how they pre-process the data, how they choose between different statistical models, or how they choose the inference criteria. If you just consider 5 decision points, each having 5 plausible options, we easily end up with more than 3,000 acceptable analysis pipelines. And as I said, very often, only one of these 3,125 pipelines is reported. Okay, you might still think that this may be not a problem if all alternative acceptable analysis paths drive us to the same conclusion. Let's call it conclusion A. But the available evidence suggests that sometimes the analysis paths really yield different results. For example, at the beginning of the COVID pandemic, the UK scientific panel has 9 teams to calculate the reproduction number R for COVID-19 infections. Although seemed to be a consensus on the direction of the effect, the lower bound of the most optimistic estimates suggested that the pandemic actually was retreating, while, by contrast, the most pessimistic estimate indicated a very rapid spread. And the uncertainty across the 9 teams was larger than the uncertainty within any one of the teams. But this is not just an isolated case. In a wonderful study led by Rotem, published in Nature, 70 independent teams analyzed the same data set coming from an fMRI study, and no 2 teams chose identical workflows, but the conclusions were also contradicting. In a study led by me, where we tested how cash transfers affected the cognitive performance of the poor, we also found that both the strength and the direction of the effect depended on the analytical decisions that we made. I think now you can guess what the results were, where a study led by Felix, they tried to analyze share trading data. So all these studies suggest that not in all cases, there's a single uniquely appropriate analysis to answer a given research question, and often plausible analysis yield different conclusions, and even researchers disagree what's the most appropriate analysis. Okay, But just because I showed you that there is a problem, the problem is present in some studies, it doesn't mean that it doesn't imply that it's present in all studies. So far, we have only scattered evidence across disciplines. We do not know whether the severity of the problem varies by individuals, methods, designs, or different disciplines. Consequently, we don't know how much we can trust the published empirical results, given such uncertainty. So, the first main goal of our initiative is to estimate the prevalence and the severity of the problem in social and behavioral sciences and understand when it really matters. Later investigation could be extended to other disciplines such as medicine and geography, but here, this is not our focus yet. Before I get to our second main goal, here comes another confession from me. We do not have yet the ultimate solution to deal with analytic uncertainty. Prior research has suggested 2+1 main type of solutions. In the multiverse style analysis, typically one analyst systematically performs all potential analysis pipelines. In a multi-analyst study, several analysts independently follow their own preferred analytical approach, while in the combined approach, multiple analysts independently perform all potential analysis pipelines. So, while the multiverse analysis can save resources and can be applied even when data cannot be shared, the multi-analyst approach can safeguard against researchers' biases and blind spots. Clearly, the combined approach is the strongest, but it would put unrealistic burden on the researchers. So our second goal is to reveal how these different approaches can map the analytical variability compared to each other. This has never been done before. And if we know the answer to these first two questions, then we can develop actionable recommendation and work on cultural change. Okay, to be able to make generalizable statements, we need first a large and diverse set of papers. And to conduct variability mapping analysis, we need data sets and hypotheses to test for each of the papers. The good thing is that as part of our ongoing Multi-100 project, in collaboration with the SCORE project and years of heroic work, these things are already prepared. 100 papers has been already chosen through a stratified sampling methods covering the main disciplines of social and behavioral sciences. And the corresponding data sets for each paper are also ready to be shared for the analysis, and the testable claim has been selected for each data set. Here, we propose using the same set of papers, as it mitigates the risk and the required resources associated with this project, and we will be able to create a richer data set. Okay, what we need to do next is to recruit and work together with 500 experienced analysts. Although it looks like an impossible project, in our case, it's not, because we have already gathered global interest with our prior study. More than 1,100 researchers from 50 countries expressed interest at conducting the analysis with us. What will happen? Each co-analyst will be assigned to one paper and will be provided with access to the corresponding dataset. And the task of the co-analyst will be to test a given claim by conducting a multiverse style analysis of the corresponding data. Co-analysts will be explicitly asked to consider the decision points and run all reasonable and plausible scenarios, how they can complete with missing data, outliers, and so on. But each paper will be analyzed not just by one, but by 5 analysts. We are in a unique position now to execute this gigantic project because all of us have led prior big team science project. For example, in the Multi-100 project, I led more than 500 collaborators. Each of the core members has published as lead authors in top journals such as Nature or PNAS. We have more than 1,000 researchers eager to work on the problem, and we have also the 100 studies ready. So, but what will be the main output of the projects when we will finish? First, we will create a large, unique open access data set where we and other researchers working on this problem can answer research questions regarding analytic variability and publish the results. In the dataset, we will have all kinds of analysis, all approaches, the multiverse, the multi-analysis, and the combined approach from 500 different people for 100 papers. That way, we will be able to learn several things. How the analytical variability in each paper, how the variability differs between disciplines, individuals, and methods. We can compare how different methods perform, so we can reveal which type of analysis should be recommended under which circumstances. but we know that publishing a paper or two won't save the Earth. Instead, what we need is a cultural change. And to promote that, we will develop methodological recommendations. First, for research scientists on how to explore and report analytical variability. Second, to journal editors to adapt their guidelines. Third, founders for evaluation of grant proposals, and educators and statistic teachers. Importantly, one of the largest obstacles of change are always researchers' old habits. And to accelerate a shift in that, we will train the 500 participating researchers on how to execute and report variability mapping techniques. Once we do all that, our hope is that more and more researchers will explore analytical variability in their papers, and that way we can increase the transparency and reliability of future research. So when our own PhD students later will start their experiments, they can avoid the pitfalls that we fall into. Thank you very much.